Hi everyone, I'm Ben. Welcome back to my YouTube channel. In today's video, we are diving into part 4 of the NVIDIA Modulus series, the scalar transport to the advection diffusion problem, a heat dissipation case. We will compare the temperature, velocity, viscosity, and pressure, analyzing the difference between modulus and open form. This will help us understand how to implement fluid dynamics and heat transfer into a physics-involved neural network. This case is referenced from the NVIDIA Modulus documentation. And additionally, you can download the OpenFOAM result from the NGC catalog. And also, I have published my reproduced documentation and code on my GitHub page, so you can download it anytime and I will continuously update it. And this problem is simplifies a 2D heat transfer scenario. In this case, we will see 3 heatsink fins in the middle and a channel and a non-slip, a diabatic wall on the top and the bottom. The inlet has a parabolic velocity profile and the temperature is 293 degrees and the outlet pressure is set to be 0. So the parabolic velocity will look like this in the inlet side. Just to clarify, this is not a conjugate heat transfer problem. We won't be dealing with solid heat transfer in this case. In this heatsink, we will treat it as a fixed temperature boundary with the heatsink fixed at 350 degrees. In actual product design, we will know the power at the base of heatsink and we want to understand the resulting temperature in the heatsink. However, in this setup, we cannot determine the exact temperature on the heatsink itself. In the next video, we will tackle the conjugate heat transfer problem. The concept covered here in fluid dynamics and heat transfer will prepare us for a deeper dive. Here, part 5. In this part, we dive into the equivalent equation. We use the Navier-Stokes equation, which is based on the conservation of mass and momentum concept we introduced in part 2 of the Lie-driven cavity example. And we also apply the zero equation turbulence model, which is covered in part 3 videos, where we modify the viscosity to mu effective viscosity and incorporate it into the Navier-Stokes equation. This adjustment helps us improve the accuracy of turbulence modeling. So we change the mu to mu effective and implement to Navier-Stokes equation. In the advection diffusion equation, which governs heat transfer, we first define a new variable C to normalize the temperature. Then we apply the diffusion equation to model heat transfer by calculating how temperature spread over time and space. This equation consists of 3 key components. Evolution terms describe how temperature changes over time, and the advection term accounts for heat transport due to fluid motion, and the diffusion term models heat spreading due to thermal conduction. In our 2D domains, we solve this equation to reach an equilibrium state where the temperature distribution stabilizes. For a deeper understanding, you can check out this video on the scalar transport equation. In part 3, we will dive into the code workflow. First, we define the geometry, including the channel and 3 fins. Also, we set the heat sink and base temperature and specify key parameters such as kinematic, viscosity nu, and diffusivity. So this is the 2D dimension problem. So we have symbol x and symbol y, and using the channel 2D function to generate this rectangular face. So we have bottom left corner and top right corner, and also generate the heatsink. So this is the lower heatsink, and use for loop to generate another 2 heatsink. And also using the line to generate the inlet and the outlet boundary. And the neural network nodes part, we have zero equation, which is still going to change new to new effective and implement it to Navier-Stokes equation. And also we have Advection Diffusion equation to deal with the heat transfer problem. And also the gradient normal is a gradient normal to deal with the adiabatic wall boundary. And we also have the normal dark vector problem function. We will discuss this later. And so in the flow net, we input key is x and y, and the output key is velocity and pressure. And in the heat net, we have the x and y, and output key is c, which is temperature. So node is to make every node together. And in the constraint, we have the inlet is a parabolic function, which is here. We have discussed this before. So we have the inlet parabolic u, and the velocity v is 0, and the temperature is to be normalized to 0 here. So we know we have temperature inlet minus temperature inlet, so the C is equals to 0. And the outlet, we have pressure to be set to be 0. And in the heatsink wall, the velocity is 0, and the temperature is set to be normalized to 350 and minus 293. So this is a fixed temperature in the heatsink wall. And also in the channel wall, we have the boundary velocity is to be 0, and the normal gradient C is to using this function. So the gradient temperature in the adiabatic wall is set to be 0, which means the partial t partial x and the partial t partial y should be equals to 0. And the interior flow, we have the continuity and momentum set to be 0. This is Navier-Stokes equation. And also the interior heat advection equation is set to be 0. And in this case, we use a normal vector function to enforce integral continuity, adding the constraint that help us to speed up convergence. First, we define an integral line across the channel, ensure that the mass flow rate along this vertical line remains the same. This condition allows us to improve our calculation. In part 4, we dive into code implementation, and you can go to my GitHub page and download this Python file and open your Jupyter notebook. So we need to use Modulus scene example 3D 2D, and you can copy this for open form CSV file and these 3 Python file into this page. So yes, we have open form CSV file, and we have the heatsink picture Python file and the heatsink 2D picture IPY Python file, and also the TensorBoard file IPY notebook. And let's check the heatsink picture Python file. So in this file, I just add and modify this custom validator plotter. This is to generate this image, so we can see the Modulus prediction and open form result, which is the true solution, and we can check the difference, and this image will plot on the TensorBoard. True is open form result from the CSV file here, and also we have the P prediction. This is generated by NVIDIA Modulus, and we have the P difference, which is using true solution to minus prediction. And we also set up the color bar limit. So yes, and also we define the heatsink mask, because when we plot, we will get a whole region of this in this channel. So we need to mask heatsink. Yes, and in here we need to change this validator plotter and the batch size and require grid. Yes, that is all I modify in the original heatsink Python file. Okay, so you can run, and we can open the TensorBoard to check the output result. So in here, you can monitor the every step loss. And also the important thing is image. So we can know the every step. So if you look at this pressure, when you train more steps, the difference will be much closer to the open form true solution. Yes, so you can see the U is getting more similarity. Yes, I think if I train more steps, I will get more similar result. Okay. And I also provide some code in this IPY notebook, and this can plot the image directly from the Jupyter notebook. and I provide this code on my GitHub website, so you can using this code to plot if you want. Okay, and I also using the OpenFOAM to simulate this problem. But I think this also has some problem, like I don't using the parabolic inlet. I have no idea to use that. So if you have some idea, you can share with me. Okay, so I think that is all today's video, and I hope you learned something in this video. Bye bye.